Microsoft just told the world it built a computer chip powered by a particle that might not even exist. And the most unsettling part isn't the science, it's the timing. Because while Microsoft was celebrating, its two biggest rivals had already lapped it. By the end of this video, you'll understand exactly why some of the most respected physicists on the planet think Microsoft may have already lost the most important technology race of the century, and why the company keeps making headlines anyway. Let's start with what Microsoft actually announced. In June 2026, at its Build Developer Conference, Microsoft unveiled Majorana 2, a new quantum chip built on what the company calls a topological core. This isn't Microsoft's first attempt. Back in February 2025, the company revealed Majorana 1, placing 8 so-called topological qubits on a chip it claimed was designed to eventually scale to 1 million. The pitch was audacious from day one. Instead of building quantum computers the way everyone else does, Microsoft bet on a fundamentally different, far riskier approach. One built around a theoretical particle called the Majorana fermion, first predicted by physicists nearly 90 years ago, and never conclusively observed in nature until, Microsoft claims, now. Here's why that bet matters so much. Most quantum computers today, the ones built by Google and IBM, use superconducting qubits, which are notoriously fragile. They lose their quantum state, a process called decoherence, in fractions of a second, and correcting for the constant stream of errors this creates requires mountains of extra hardware. Microsoft's topological approach promised something different. Qubits that are stable by design, built directly into the physics of the material itself, supposedly needing far less error correction to function reliably. If it worked, it could leapfrog the entire industry. That's the promise. Now let's talk about the problem. With Majorana 2, Microsoft claims a genuinely staggering improvement, a 1,000-fold increase in qubit reliability compared to its predecessor. The company says its qubits now survive for an average of 20 seconds, with some instances lasting up to a full minute, achieved partly by swapping the material's superconductor from aluminum to lead, which better resists disruption from radiation and cosmic rays. Microsoft has also dramatically accelerated its own public timeline, now targeting a scalable, commercially valuable quantum computer by 2029, 4 years earlier than its original roadmap suggested. On paper, that sounds like a company sprinting ahead. In the physics community, it landed very differently. Almost immediately after the announcement, skepticism poured in from researchers who were not in the room. Henry Legg, a physicist at the University of St. Andrews, has been one of Microsoft's most vocal critics, arguing that the new data still doesn't prove a working topological qubit exists at all. Demonstrating a genuine qubit requires two distinct kinds of measurements, and critics point out that Microsoft's new paper only presents one of them. Legg's blunt assessment was that nothing in the presented data proves the existence of a topological qubit or Majoranas in these devices. That is about as damning a statement as you can get from a working physicist, aimed directly at one of the most valuable companies on Earth. To be fair, the reaction inside the field hasn't been universally negative. Kartik Agarwal, a physicist at Argonne National Laboratory, described Microsoft's new measurement method as genuinely supporting the case that these are real Majorana particles, calling it fantastic progress. So the scientific community isn't unanimous. It's split, with some researchers cautiously encouraged and others openly unconvinced. But here's the pattern worth noticing. This is now the second time in a row that Microsoft has announced a quantum breakthrough and been met with exactly the same response, excitement from the company, and immediate, pointed pushback from independent physicists asking for stronger proof. Now let's zoom out, because the real story here isn't just about whether one chip's data is convincing. It's about what everyone else was doing while Microsoft was defending its lab results. Google's quantum team hasn't been sitting still. Its flagship processor, Willow, made headlines in December 2024 by demonstrating something called below-threshold error correction, a major milestone, meaning that as you add more physical qubits to the system, the error rate actually goes down instead of up, which is essentially the holy grail of making quantum computers scale. In 2025, Google went even further, publishing a landmark result in the journal Nature showing what it called verifiable quantum advantage, using an algorithm named quantum echoes, reportedly running roughly 13,000 times faster than the best classical supercomputer on Earth could manage the same task. IBM, meanwhile, has been playing a completely different game, and arguably a smarter one for the real world. Rather than chasing headline-grabbing single breakthroughs, IBM has published a detailed, almost boringly specific roadmap stretching out to the end of the decade. In late 2025, the company shipped its Nighthawk processor, a 128-qubit chip built around improved connectivity between qubits, and it's already planning to link multiple Nighthawk chips together, aiming for roughly 1,000 connected qubits within just a couple of years. IBM's stated target is verified quantum advantage by the end of 2026, and a fault-tolerant quantum computer, meaning one reliable enough for serious commercial use by 2029. That's the exact same year Microsoft is now targeting, except IBM has been operating an open cloud platform this entire time, letting outside researchers and companies actually run experiments on its hardware today, not in some future promised year. And that gap, access versus ambition, might be the single most important difference separating these companies right now. Google's quantum computing service remains in a limited preview, mostly reserved for vetted research partners rather than the general public. Microsoft's chips remain lab demonstrations, impressive on a slide deck, but not something a business can rent time on to actually solve a problem today. IBM, by contrast, has spent years building an accessible ecosystem around its quantum hardware, meaning that even if its chips aren't the flashiest on paper, they're the ones people are actually using right now to learn, test, and build. There's a deeper financial story tangled up in all of this too, and it's worth understanding because it explains why these announcements generate so much noise. When Google announced Willow's breakthrough error correction result, it didn't just make scientific headlines, it triggered what analysts later described as a full-blown market mania around quantum computing. Stocks. Investors piled into anything with the word quantum attached to it, valuations soared, and for a moment it looked like the technology had arrived. But financial analysts have since pointed out an uncomfortable truth sitting underneath all that excitement. Willow was completing benchmarks that no commercial customer was actually paying for. Microsoft's Majorana chip was, in the analyst's own words, a research prototype. And IBM's fault-tolerant roadmap wasn't nearing its finish line. It stretches all the way through 2029. The gap between the narrative investors were buying into and the actual revenue being generated wasn't a small crack. It was described as a chasm. So where does that leave Microsoft specifically? The company is making one of the boldest technical bets in the entire industry, wagering that topological qubits, if they can actually be proven to work reliably, could eventually need far less error than Else's approach, potentially making Microsoft's system dramatically more efficient at scale. If that bet pays off, being first with a genuinely stable topological qubit could be worth more than being first with any number of noisy, error-prone qubits everyone else is racing to stack up. That's the case for patience. But it's also exactly why the skepticism matters so much right now. Betting everything on a particle that respected physicists still say hasn't been conclusively proven is an enormous gamble. And every year that gamble takes to pay off is another year competitors with less exotic, already working approaches pull further ahead in the metrics that actually matter today. Qubit count, error rates, and paying customers. It's also worth remembering that Microsoft isn't purely a hardware company chasing this race for bragging rights alone. Alongside the Majorana 2 announcement, the company also pushed forward its Microsoft Discovery platform, an AI-driven research tool that reportedly helped accelerate the chip's own development by analyzing over 2 decades of quantum research data, identifying issues, and streamlining workflows that would have taken human researchers far longer to work through manually. In other words, Microsoft is using its dominant position in artificial intelligence to try and buy back time in a hardware race it may be losing on raw physics alone. Whether that AI-assisted approach can meaningfully close the gap against Google and IBM's more conventional, already scaling architectures remains genuinely unclear, and that uncertainty is exactly what makes this such a fascinating story to watch unfold in real time. Zoom out even further, and there's a bigger industry pattern hiding underneath all 3 companies' announcements. Nobody actually agrees on which architecture will win. Google is betting on superconducting qubits with below-threshold error correction. IBM is betting on the same underlying superconducting approach, but focusing obsessively on connectivity and near-term commercial access. Microsoft is betting on an entirely different physical phenomenon that may or may not even exist in the way the company claims. And that's before you even factor in companies like IonQ and Quantinuum, who are betting on trapped ion technology instead of superconductors altogether, or Xanadu, pursuing a photonic approach using particles of light. This isn't a 2-horse race, or even a 3-horse race. It's an all-out scramble between fundamentally different bets on the very laws of physics. And right now, genuinely nobody knows for certain which one will cross the finish line first. If you enjoyed this breakdown of one of the strangest tech races happening right now, hit that like button. It genuinely helps this channel keep covering stories like this one before they hit the mainstream. And if you want to stay ahead of where this industry is actually heading, instead of just reading the press releases, subscribe so you don't miss the next deep dive. To really understand why physicists are so cautious about Microsoft's claims, it helps to understand what a Majorana particle actually is and why chasing it has been considered such a long shot for so long. Predicted back in 1937 by the Italian physicist Ettore Majorana, the particle is theorized to be its own antiparticle, an incredibly strange property that most particles in the universe simply don't have. For nearly 90 years, this remained purely theoretical, a mathematical curiosity discussed in physics papers, but never definitively observed in a laboratory. Microsoft's entire quantum strategy hinges on being able to coax something that behaves like a Majorana particle into existing at the edges of specially engineered nanowires, then using the strange properties of that particle to store quantum information in a way that's inherently more resistant to the outside world's interference. It's an elegant idea on paper. Actually proving you've built it, rather than something that merely looks similar in certain measurements, has turned out to be brutally difficult, and that difficulty is exactly where the current scientific dispute lives. This isn't the first time Microsoft has walked into this exact controversy either, and that history matters more than most casual observers realize. Back in 2018, a Microsoft-backed research team published a paper in the prestigious journal Nature claiming strong evidence of Majorana particles in a similar nanowire device. It was hailed at the time as a landmark result. Then in 2021, after other physicists tried and failed to reproduce the findings, the researchers were forced to retract the paper entirely, acknowledging that the original data had been selectively presented in a way that made the signal look far more convincing than the full dataset actually supported. That retraction sent a shockwave through the small, tight-knit community of physicists working on topological quantum computing, and it's the exact reason why so many of them are demanding complete, transparent data from Microsoft now, rather than simply taking the company's word for it a second time. That backstory is also why Legg's specific complaint about X and Z measurements matters so much more than it might sound on the surface. In quantum mechanics, fully characterizing a qubit's behavior requires measuring it along different axes to confirm it's behaving the way theory predicts, not just producing a signal that resembles the right answer in one narrow test. Microsoft reported both types of measurement with its original Majorana 1 chip, and many experts still weren't convinced by what the company showed. With Majorana 2, critics note the new paper leans on only one of those two measurement types. To an outside observer, that might sound like a minor technical footnote. To a physicist who lived through the 2021 retraction, it looks uncomfortably familiar. A company presenting a partial picture and asking the world to trust that the rest of the picture, if it were shown, would look just as good. None of this means Microsoft is wrong, and it's worth being fair about that distinction. Being cautious about extraordinary claims isn't the same as declaring them false. Physics has plenty of examples where a genuinely correct discovery faced years of justified skepticism before enough. Independent verification finally settled the debate. It's entirely possible Microsoft's team is sitting on a real working topological qubit and simply hasn't yet published the complete dataset that would convince every skeptic in the field. But possibility isn't proof, and in a field this technically demanding, with this much money and reputation riding on the outcome, most serious physicists have learned the hard way not to extend the benefit of the doubt until the full, replicable evidence is actually on the table. It's worth pausing here to translate some of these numbers into something a little more tangible, because raw qubit counts and coherence times can sound abstract if you don't work in the field. Microsoft's claim of qubits lasting 20 seconds on average, with some reaching a full minute, represents a genuinely enormous jump compared to earlier error correction overhead than anyone. Topological qubit attempts, which typically survived for mere fractions of a second before losing their quantum state entirely. To put that improvement in perspective, Microsoft itself compared it to inventing a phone battery that used to die within a single day, suddenly lasting for nearly 3 years on one charge. Numbers like that explain why the announcement generated so much genuine excitement inside the company, even as outside physicists remained focused on a different, more fundamental question. Does the underlying particle actually exist the way Microsoft says it does, regardless of how long it appears to survive in these specific tests? Meanwhile, the rest of the industry has been quietly building infrastructure, while this specific controversy has played out in scientific journals and conference stages. Amazon, often overlooked in these conversations, because it isn't building its own quantum chips the way Microsoft, Google, and IBM are, has instead built Amazon Bracket, a cloud platform that lets businesses experiment with multiple different quantum hardware providers without committing to any single company's architecture. That hardware-agnostic approach might end up being just as strategically important as any individual chip breakthrough, because it means customers can start building quantum-ready skills and workflows today without betting their entire strategy on which physical approach eventually wins. Honeywell, through its Quantinuum subsidiary, has taken yet another path entirely, focusing on trapped ion technology and currently operating what's widely regarded as one of the most accurate commercial quantum systems available anywhere in the world right now, even if it hasn't generated nearly the same volume of headlines as Google or Microsoft. All of this paints a picture of an industry moving in several directions simultaneously, each convinced its particular bet on the underlying physics is the one that will eventually scale. That's actually a healthy sign for the field as a whole, even if it makes for a confusing headline every few months. Diversity of approach at this early stage means the eventual winning architecture, whichever one it turns out to be, will likely have been genuinely stress-tested against several serious alternatives rather than emerging by default because it was the only serious contender in the room. But for Microsoft specifically, operating as the company with arguably the most unconventional bet and the most public scientific controversy trailing behind it, that diversity is a double-edged sword. It validates the broader idea that unconventional approaches deserve serious investment, while simultaneously ensuring that every one of Microsoft's announcements will continue to be measured against rivals who are shipping accessible, working hardware right now, not hardware that might work once enough skeptics are finally convinced. There's also a talent and funding dimension to this race that rarely makes it into the headlines but shapes everything happening behind the scenes. Every major quantum lab is competing for the same small, highly specialized pool of physicists capable of doing this kind of work, and a company's public reputation genuinely affects its ability to recruit the best people in the field. A string of skeptical peer reviews doesn't just create bad press, it can make top researchers think twice about joining a team whose flagship results keep getting publicly challenged, while a company like IBM, with fewer dramatic claims but a longer track record of quietly delivering on its stated roadmap, may find it easier to attract exactly the kind of careful, methodical scientists this field desperately needs. The company has now publicly accelerated its own roadmap twice, first committing to a 1,000,000-qubit vision with Majorana 1, then compressing its timeline to 2029 with Majorana 2. Every acceleration raises the stakes for the next announcement, because each time Microsoft speeds up its public promises, it also shrinks the amount of time it has to actually deliver conclusive proof before investors, customers, and rival physicists start asking harder questions. Google and IBM, by comparison, have been far more conservative in their public timelines, which paradoxically gives them more room to kind of scrutiny hanging over every incremental update. There's also a quieter danger buried in Microsoft's approach that's worth sitting with. Science has a long, well-documented history of extraordinary claims that ultimately couldn't be replicated, and quantum computing specifically already has scar tissue from this exact situation. Microsoft itself was forced to retract an earlier scientific paper years before Majorana 1 was even announced, after outside physicists couldn't reproduce results the company had published. That history is precisely why so many researchers are demanding stronger, more complete evidence this time, before accepting Microsoft's claims at face value. And it's precisely why the current skepticism shouldn't be dismissed as reflexive doubt. It's informed caution, earned the hard way. So is Microsoft actually losing the quantum race? The honest answer is that it depends entirely on which race you think is actually being run. If the race is about who can put the most working error-corrected qubits into the hands of paying customers the soonest, Microsoft is clearly behind both Google and IBM right now, and the gap in accessible, real-world usage is not close. But if the race is really about who eventually builds the most efficient, scalable architecture over the long run, the game isn't over. It may not even be at halftime yet, and Microsoft's contrarian bet could still theoretically pay off in ways that make today's head start from its rivals look far less decisive in hindsight. What is certain is that the pressure on Microsoft to produce undeniable, independently verified proof is only going to intensify from here, and the entire industry, along with a growing number of skeptical physicists, is watching extremely closely for what comes next. If this kind of story is exactly the type of tech breakdown you want more of, make sure you've liked this video and subscribed to the channel, because there's a lot more of this coming and you really don't want to miss it. You think actually wins this race? Microsoft's exotic long shot, Google's error correction lead, or IBM's steady, accessible roadmap? Because the debate in the comments on stories like this one is honestly half the fun of covering them. And if there's one thing worth remembering the next time a flashy quantum headline crosses your feed, it's this: a press release is not a peer-reviewed result, and a peer-reviewed result is not the same thing as a product you can actually buy or rent time on today. The distance between those three things is exactly where most of the confusion around this entire industry lives, and now you know exactly where to look when the next big announcement inevitably drops. Thanks for watching, and we'll see you in the next one.